My name's Zach, and I'm really excited today to present on some of the work I've done so far during my PhD, which is mostly looking into machine learning of the chemical inventory and rare isotope logs of the protostellar source IRAS 16293-2422b. So first of all, let me give just a very high-level overview of what supervised machine learning for regression is. So the overall goal in this process is to learn a set of model parameters that can be best used to map some input features, some x values, to some relevant properties, some y values. Just the simplest and oversimplified possible example of this process is just 2D linear regression, something that could be modeled by y equals mx plus b. And what you do in this process is you provide the model with training data in the form of x-y pairs. And what it does is it learns the model parameters, in this case the m and the b, that can best map those inputs to those outputs in a way that minimizes some sort of loss function. And while this is a very oversimplified view of this whole approach, it can also be very effective for high-dimensional inputs and also include very complex nonlinear models as well. So now getting into the problem that I'm trying to tackle with this approach. So the overarching goal behind most of the work I've done so far is suggesting likely molecular candidates for detection in various regions of space. So let's first take a step back and ask the question, why do we even care about interstellar molecules? So because we're looking all the way out in space, we're not fortunate to be able to throw a thermometer in a reaction beaker, easily observe some sort of physical change during a reaction. Instead, in order to trace the physical properties and evolutionary history of interstellar sources, we oftentimes rely on the molecules that we detect along with the properties of said molecules. And just a couple of examples, D to H ratios provide information about the temperatures of the environment during molecular formation, and the detection of SIO can trace things like stellar outflows or shocks. So in the past, if we wanted to model molecular abundances and use this to predict new molecules for detection, we relied heavily on astrochemical models. And these, as can be seen on the screen, are vast networks of interconnected reactions, each reaction having its own rate constant, and ultimately, they can be used to derive the time-dependent molecular abundances of these species. And while these are excellent tools to gauge our current understanding of the specific chemical processes in space, there's a couple of drawbacks. First of all, in order to add a new molecule or reaction to the network, we oftentimes rely very heavily on chemical intuition. Additionally, the rate constants that are inputted into the networks are oftentimes either extrapolated or approximated, and the uncertainty that comes along with this when you propagate it through the whole network can result in some very uncertain or inaccurate modeled abundances. And finally, it's just difficult to include new molecules. In order to add a new molecule to the network, you have to include every single reaction that could create the molecule, as well as every one that could subsequently destroy it. So that's a difficult and oftentimes inefficient process. So in response to these predictive shortcomings, a previous postdoc in our group, Dr. Kelvin Lee, developed a machine learning method that's able to predict and model molecular abundances in space without requiring these complete networks. And instead, molecular abundances are expressed purely in terms of a chemical vector space. So in this process, the first step is you need to collect telescope data toward a specific interstellar source. From this line survey, you'll be able to decipher which molecules are present, along with the abundances or column densities of said molecules. Following this, for any machine learning application, you need to vectorize your input. So we have to make molecular feature vectors out of the molecules we're detecting. To do this, we utilize the Mol2Vec algorithm, which is an unsupervised algorithm that creates context-aware substructure vector representations that can be subsequently summed to form molecular feature vectors. So at this point, we have our molecular feature vectors, our inputs, as well as our relevant column densities, our outputs. And what we do, as mentioned previously, we input this into a machine learning model that learns the best way, the model parameters to map those molecular features to the relevant column densities. And this is just a figure from the initial paper. And what it shows is that a very simple, regularized linear regression machine learning method, a ridge regression model, is able to far outcompete even the state-of-the-art Gotham Nautilus astrochemical model in reproducing and predicting the chemical abundances in the TMC1 dark molecular cloud. So while Kelvin's initial work was a fantastic proof of concept that this method can, in fact, effectively model and predict molecular abundances in space, there's a number of things that just remain simply untested. First of all, untested outside of dark molecular clouds. So the initial work was focused on the TMC1 dark molecular cloud chemical inventory, and this is a very cold and quiescent region of interstellar space. So we also want to ensure that these same methods can also apply to warmer, more turbulent protostellar sources. And for this, we looked at the class 0 protostellar binary, IRAS 16293b. This is an especially attractive source because it has a very dense molecular line survey, and it's been studied extensively with interferometric data. It's also vital that we can model the abundances in both these cold, dark clouds and the warmer protostellar sources, because understanding the chemical inventories of these two different sources allows us to investigate how the chemistry actually evolves as a star is forming. Additionally, in part due to the shortcomings of the Multivec algorithm, there were initially no isotopologues included in the dataset. However, IRAS 16293b consistently shows very high levels of isotopic substitution. As a result, in order to fill out the dataset, we felt the need to include these molecules. Additionally, as mentioned previously, isotopologues provide information about the temperatures and timescales of molecular formation in space, and therefore being able to model these ratios effectively with this machine learning method would provide a straightforward and efficient way to gain additional astrochemical insight. So in order to include these isotopologues, we added hand-picked isotopolog descriptors at the end of our Multivec representations, and more specifically, we added 19 extra vector dimensions that denoted which specific minor isotopes are substituted into the molecule, along with the chemical environment of said isotopic substitution. So just as an example, 3 of the vector dimensions denote whether the 13 carbon is sp, sp2, or sp3 hybridized, and we chose this feature because, as you can see, it has a notable impact on the mean 12C to 13C ratio of the molecules in this source. So now getting into some results, we trained both a Gaussian process regression and Bayesian ridge regression model to map the molecular features of the column densities. And what we were ultimately able to see is that the models are able to both effectively model the molecules provided to it in the training set, but also extrapolate quite well to yet unseen molecules in the testing set. Additionally, because we included isotopologues in our data set, we wanted to see how well these models are able to reproduce the column densities and isotopic ratios of the molecules in this source. So what you can see on the top row of the deuterium and 13C substituted isotopologues, using 5-fold cross-validation, the column densities are very accurately modeled. Once you extrapolate this out to actual isotopic ratio predictions, these are much more sensitive to small changes in column densities. As a result, a small error in the column density prediction can result in a large isotopic ratio error. So the bottom row of actual isotopic ratios is slightly less precise. However, just because of how nuanced the process of isotopic fractionation is in space and how simple our encoding is, we're very encouraged by these results that we're able to very accurately model the column densities of these isotopically substituted species. So as mentioned previously, due to the strong performance on the testing set, we have some sort of confidence that these models can extrapolate to yet unseen species. And as a result, we proceeded to input about 90,000 astrochemically relevant molecules into the trained models to see which undetected species are likely the most abundant in this source. And on the bar chart on the screen, you can see the top 10 predicted abundance molecules toward IRAS 16293b, and there's 2 things to point out here. First of all, 3 of these molecules, namely hydrogen peroxide, ethane, and carbon dioxide, have all been previously detected in different regions of space. Additionally, something you may notice in the bar chart is that many of these molecules are very oxygenated and fairly saturated hydrocarbons, and this is also a good sign because when looking at the actual chemical inventory of these sources, or this specific source, the most abundant detected molecules are also these very oxygenated hydrocarbons. So not only is it learning to predict known interstellar molecules, but at the same time, it's narrowing down to the correct region of chemical space relevant to this source. So, as I mentioned, these 10 molecules have not been previously detected in this source, and the reason for that in many cases is just simply a lack of rotational spectra being taken in the lab. So now, next steps is we want to take that next step forward and collect the rotational spectra of some of these predicted high abundance molecules that can be searched for in these protostellar sources. One of particular interest is circled on the screen, methoxyethanol. And methoxyethanol is in the same chemical family as both methoxymethanol and methoxyethane, which have been detected in high abundance toward IRAS 16293b. But not only is this molecule chemically similar to several that have been seen before, but we also have some sort of mechanistic reason to believe it may be present. So methoxymethanol has been shown to form via reaction of the CH3O, the methoxy radical, with CH2OH on grain surfaces. So the high abundance of methoxymethanol also suggests that in the prestellar phase of the source, that the methoxy radical was highly abundant on these grain surfaces. As a result, it could feasibly react with the other high abundance organic radicals in the source, and we therefore believe that the methoxylated versions of these high abundance organics in the source may be strong targets for astrochemical study. So next step is use chirp pulse Fourier transform microwave spectroscopy to study the rotational spectrum of this molecule, subsequently use the laboratory spectrum to search for this molecule in various protostellar sources, and upon its detection, learn more about the chemistry of this highly abundant methoxy radical. So that's all the work I've done so far, as well as what I'm working towards. I'd like to say a big thank you to my group shown on the screen. The picture on the right is us in the Green Bank Telescope, which is a very cool experience. I definitely recommend if you have the opportunity to travel there. But thank you for listening, and I'd be happy to take any questions you may have.